All right, I think I'm on. Okay, welcome to the first Game AI session of the conference. The Game AI track is a pretty big one. There's 4 sessions happening each day this week. And we have 4 great papers today. Starting, I'm going to be pasting the information if you want to follow along with the paper in both this chat and the Discord chat. So our first paper is by 4 people from UC Santa Cruz, and I believe Max is presenting. I'm not 100% sure.
They actually sent in a video, so I think I will just play it.
Okay, okay.
And
Sounds
then, yep. Just give me a second.
Expressive Intelligence Studio at UC Santa. Hello, my name is Max Karminski. I'm a PhD student in the Expressive Intelligence Studio at UC Santa Cruz. Today I'm going to be talking about Why Are We Like This, a co-creative storytelling game that uses artificial intelligence and social simulation to support player co-creativity in telling a story with other players. This is a game that Melanie Dickinson, my collaborator, and I have been working on for about a year now. In this talk, I'm going to go into some background as to what it is that we hope to build and why, talk about some design goals, then give a design overview of what we built so far, and then talk about 3 key contributions that I think are sort of the most interesting things about why we like this so far from an AI and a design perspective. So to give a little bit of background, Why Are We Like This was originally conceived of in part as a successor to Bad News, a game that actually came out of our lab a couple of years ago, in which there's a sort of small American town that's been generated through years and years of social simulation, and you interact with a succession of characters in this town in hopes of finding the next of kin of someone who has recently died and delivering to them the bad news. In so doing, you interact with Ben Samuel, who is the actor on the right-hand side of the screen here. And Ben is sort of portraying the different characters in this town as you interact with them. Meanwhile, James Ryan, is on the left-hand side of this partition at a console with access to the complete history of the small town that's been simulated, and feeding Ben information about the character you're currently talking to, which can include things like their personality traits, so Ben knows how to portray them, but also things like their relationships with other characters, and nuggets of interesting sort of information about the history of the town that might sort of be useful in weaving a story about what's going on in this town overall. And through this collaboration of 2 expert participants, Ben and James, the naive participant who is the player who's coming in, and then also the simulation, this tends to produce a lot of really interesting emergent stories. However, it requires these 2 expert participants to make the whole thing run. And as a result of that, we were hoping to create something that's sort of similar to Bad News, that could create a similar sort of co-creative play experience, but that is playable maybe in your home with some from your friends, people who you might know, like not requiring these specific participants to be driving the whole thing to make it run. And we were given some encouragement, I think, in thinking that this was possible by the existence and sort of the enjoyability of these collaborative storytelling tabletop RPGs, things like Microscope and The Quiet Year, in which you and some other players sit down at a table, you tell a story together, or you write a story, or you draw a map, following these very simple rules to sort of guide your co-creative process. And at the end, you've produced some artifact that tells the history of your play session, basically. So our design goals for this were an AI-assisted collaborative storytelling play experience, something similar to Bad News, but in which you didn't really need an expert present to guide the play experience, where the computer maintains consistency, perhaps by, like, for instance, using a social simulation to say, these are the things that the characters want to do right now, and they're not going to do things they don't want to do because that wouldn't make sense. Where the computer suggests things that might happen next in the story to prevent writer's block and things like that. But also where players specifically have the job of writing text for themselves to support this design pattern of what we call extrapolative narrativization, which is the thing we see in Dwarf Fortress retelling practices, for instance, where players write stories about simulations in which details of the simulation are sort of woven in, but maybe integrated or built on in ways that the simulation itself doesn't directly model. So this is what Why We Like This looks like so far. This is actually a design mock-up of the UI, but we've got something pretty close to this working as an interactive interface now. On the left-hand side, you can see a transcript of the actions that have happened so far, including both system-generated terse descriptions of actions in bold, and also longer player-generated descriptions of actions in more detail below. On the right-hand side, you can see a list of author goals, or a list of actions that the system thinks might be able to happen next, based on both what the characters want to do, and then also on your author goals in the middle, which are things that you as the players have decided should happen, and that you've sort of communicated to the system. The three key ideas that I'm going to pull out for the rest of this talk here are the use of these author goals to communicate player intent to the AI, the use of story sifting to help players make sense of all the complex things that are happening in the story world state here, and then also the use of story sifting again to implement character subjectivity by giving characters sort of ways to interpret the events that have happened in the world and build on them. So number one, these author goals here, we're going to zoom in and look like a set of author goals that have been specified here. We've got involve Bella in plot, we've got escalate progress versus order, and we've got escalate survival versus order. So these are all things that the players might reasonably want to have happen in the story that the system knows how to support in some way. In this case, involving a character and escalating tension between a couple of values, such as progress and order, that characters might hold in this story world. You can also see there's buttons for adding new author goals, for removing existing ones, and for marking existing ones as complete. And the idea is that you finish a chapter when all the author goals you've specified for that chapter are marked as complete, and then you can move on to the next one with a new set of author goals and sort of do it all over again. So this guides the action suggestions that the system provides players with. So in this case, you can see that the top action that's recommended here, Bella, argue about progress with Flora, advances two of the author goals that are present simultaneously. It both involves Bella in the plot, and it also escalates this tension of progress versus order that the players would like to see escalated currently. And then when the players select one of these actions to have happen, it gets locked in and added to the transcript. So you see the bold sort of terse description of the action up top. And then again, the sort of system or the player generated description of the action, which is sort of a freely editable text box below. Number two, the Story World Investigator is a tool for sort of figuring out what's going on in these complicated simulated story worlds where there's so much going on all the time. The idea here is that basically you run a simulation machine, the simulation machine goes burr, it produces a whole bunch of events, and then the total number of events that it produces tends to be overwhelming. And so what you need is this process of story sifting to sort of parse it down. Story sifting basically involves looking at these massive databases of events that have transpired, filtering them down to just the ones that match a certain micro-story pattern, and then raising these micro-stories to the player in some way that they can then interact with and sort of weave that into the story they're telling themselves. So in this case, the micro-story we look at might be A starts a project, a character A, the same character decides the project isn't any good, gives up on it, then a second character B comes along and talks to them about that project several times, and then because of B's interest, A finally decides to resume work on the project. So this is sort of a micro-story that could be woven into a larger plot, maybe sort of furthering certain author goals, such as showing that B and A have some degree of rapport, or maybe sort of portraying this as something good that B has done for A, or maybe as something bad if A ends up later on deciding that this project was actually a bad thing for them all along. So returning to this problem of overwhelm, what the Story World Investigator is basically a tool for taking all these massive number of events that have happened and presenting them to the user in a way that they can more readily sort of like query and find interesting emergent situations. And that includes things like looking at the history of a particular character's involvement with other characters. You can see here that you can select like different projects that have happened, different relationships. And then on the right-hand side, we've got a detailed view of the currently selected entity, in this case, Bella, a character in this story world. And we can see her values, we can see her curses, which are things that sort of like inhibit her actions in some ways, and then relationships that she has with other characters in this case are sort of summarized briefly below. And you can click on, for instance, these other characters like Anya and Flora to see more about those characters and their context in the story world. So all of this is basically a set of tools that do the same thing that James does in feeding information to Ben in a bad news play session. And then finally, we also use the story sifting technology to implement what we call character subjectivity, which is basically different characters looking at the same set of events that have happened in the story world. In this case, we're going to have two characters, Izzy and Nicole, and getting very different messages out of them, because these different characters have different personality traits and therefore use different story sifting patterns to make sense of the world. So Izzy, for instance, is looking at this set of 25 events and pulling out these three as interesting in the story sifting pattern that basically makes her say, wow, I'm so bad at this, Nicole must hate me. And then Nicole is looking at these same events with a different story sifting pattern and saying instead, Izzy does so many cool things, I wonder if they'll be my friend. And these divergent interpretations of the same events driven by story sifting and the access to different story sifting patterns produces a lot of emergent drama between these characters, and this is sort of the driving thing that moves Walt stories forward. So, altogether, in conclusion, Why We Like This is an AI-assisted collaborative storytelling play experience in which players specify author goals to influence the AI suggestions of what should happen next. Story sifting tools help players make sense of the story world and all the things going on in it, and meanwhile these characters apply story sifting to interpret the world, which leads to emergent conflict between them. I'm going to leave you off here with a sort of small system diagram of the overall Walt system, and then you can also find all the papers that I've talked about at mcrimmins@github.io. Thank you.
Yay. Thank you, Max. We have time for maybe one question, probably, and then you can continue discussion in either Discord or here. But does anyone have a question they want to ask live? All right, if no one is going to ask a question, we'll move on because we're actually a little bit behind time. So we're going to go to the second paper, which is a collaboration between people at Drexel and Rowan University called Player Modeling versus Multi-Armed Bandits, which you can get right here. And David, is that a video or?
Yes, I'm going to play it now.
My name is Robert C. Gray, and I'm a PhD candidate in digital media at Drexel University. On behalf of my co-authors, I will be presenting our research on player modeling via multi-armed bandits for the 2020 Foundations of Digital Games Conference. Our research here offers two contributions. The first is an approach toward player modeling based on multi-armed bandits, or MABs, where we will demonstrate how we formulate a player modeling problem as a multi-armed bandit problem, and use solutions from that field to both classify players and individualize a software experience for those players. Second, we demonstrate an approach for evaluating and fine-tuning our AI agent via simulation in preparation for a user study to maximize the value of that user study. But first, let's review some of our core concepts. Our main area of research is adaptive games, where we leverage knowledge of a player to change how a game functions to better serve individual players and specific design goals. This approach often relies on player modeling, where the game aims to understand characteristics of a player, such as their preferences or their capabilities, that can inform this adaptation process. Yannikakis and others have conceptualized player modeling approaches as being top-down, bottom-up, or some mixture of the two. In a top-down approach, knowledge of the domain informs the design of categories, and a set of heuristics devised by the authors of the model classify players into the pre-established categories. In contrast, bottom-up approaches are context-agnostic, discovering the categories and classifying players via AI, machine learning, or other statistical analysis of player data. Our work is informed by both of these approaches, leveraging psychology theory to provide the domain in which we will distinguish players, but relying on AI techniques rather than heuristics to perform the classification task for the individuals. Specifically, we are aiming to distinguish players according to their social comparison tendencies. Social comparison is a psychological process by which people, consciously or unconsciously, compare themselves to others in order to assess their degree of success, plan for their future success, or to feel better about their current state or situation. It is believed that some people prefer to seek out comparisons to others who are doing better than they are, known as upward comparisons, because it inspires them and gives them insight into how they can improve, while others might generally tend to seek out comparisons with others who are not doing as well, known as downward comparisons, because it can boost their confidence or provide reassurance. This and other personal social comparison tendencies are collectively referred to as the person's social comparison orientation, or SCO. Our larger project is to design a game that motivates players to engage in real-life physical activity, or PA, and we believe we can leverage this phenomenon by modeling players according to their SCO traits, where we then offer an intervention by way of presenting comparison opportunities that will appropriately motivate individual players. We aim to do this by leveraging theory around multi-armed bandits. A multi-armed bandit problem is a type of sequential decision problem, where an AI agent, sometimes referred to as a bandit, must make a repeated choice among a set of actions, we'll call them arms, that each yield some unknown reward. The agent wants to maximize their total reward over a limited number of selections, but the reward for each arm is not known until it's selected, and the rewards can vary. The agent has to decide how to split its decisions between exploring the options to learn the reward distributions and exploiting the option it believes to be the best. And research in this field has found that, given the right strategy and enough time, the agent will eventually converge on the best option. Our approach takes advantage of this by setting up the categories of the player model as arms in the MAB problem, where each arm provides a different option for a game experience. Looking to resulting player metrics as a reward measurement, we allow the agent to converge on the arm that yields the best result for the player, thereby categorizing the player within the model. In this case, the method is the model, and the bandit is simultaneously the system that classifies players and the AI that adapts the game. But let's talk about some specifics. Our plan is to use such an AI agent to guide a daily web-based intervention that aims to increase players' daily steps and motivation to engage in PA. A player logs onto a website and reports on their current PA motivation. They are then presented with 4 profiles of other players, which are fabricated but presented as real to the player. And these profiles may have more or fewer steps than the player did the previous day, measured via Fitbit. Though not known to the player, they will experience one of 3 configurations of these profiles each session. Configuration A displays 4 other profiles that performed worse than the player, facilitating only downward comparisons. B displays 2 of each, a mixture of upward and downward, and C displays 4 profiles that all performed better, offering only upward comparison opportunities. The player can select one of the profiles for additional information, prolonging the comparison activity. After they are finished, the player again reports their motivation to engage in PA in a post-test. Going back to our psychology theory, we predict that some players will tend to be affected more positively after exposure to upward comparisons, and some will do better when exposed to downward comparisons, depending on their individual SCO. We then formulate this as an MAB problem, where an AI agent will present one of these 3 arms to the user each day, and then observe their resulting steps and self-reported motivation. Higher steps and motivation will reinforce the agent's selection and encourage that arm for that player in the future, while lower steps and motivation will discourage the agent from selecting that arm for that player. Adaptive games and player modeling may always need user studies, but user studies are not always practical for tuning a player model or an AI. In our case, the details of a bandit strategy that make it more effective in specific use cases are not always known in advance. And yet, it is very important that we design it correctly. Not only are we limited in our opportunities for user studies, but the agent will be responsible for administering the intervention within our study, and will therefore have a direct impact on any outcomes. To address this, we explore a variety of potential bandit strategies via simulation. Using simulated players that exhibit behaviors reflecting what we expect of real players, we were able to adjust and ultimately establish confidence in our AI agent prior to deploying it in the user study. But there was a twofold challenge in creating these simulated players in a way that would be useful for evaluating our AI. First, we needed a method for generating steps that reflected the data we would expect from human players. Second, we needed to provision the simulated players with a representation for SCO that reacted to comparison events. For the first challenge, we leveraged existing daily human step behavior data obtained from a Mechanical Turk study by Furberg and others in 2016. Shown here is a histogram of that dataset overlaid with a probability density function of a fitted gamma distribution, from which our step generator would randomly draw to generate initial daily steps. Our second challenge, the SCO representation, consisted of a data model to portray the individual traits of the simulated player and a behavior model that determined how the simulated player reacted to social comparison events. Our data model consisted of 2 parameters, U and D, which represented the simulated player's respective affinity toward upward and downward comparison on a linear scale. This reflects the design of an SCO instrument used in psychology research, the Iowa Netherlands Comparison Orientation Measure, or INCOM. These 2 parameters then dictate SCO traits through derivative metrics. Directional preference is the proportion between U and D, and the intensity of reaction to a comparison event is modeled as the magnitude of the respective value. The SCO behavior model directs a simulated player's behavior when presented with a programmatic version of the exercise we intended to deploy to our human players. The simulated players were programmed to select one of the 4 profiles at random, weighted by their U and D values. Their choice then modified their steps and self-reported motivation based on the magnitude of their parameters. So how does the AI agent react in response to these simulated players? Many bandit strategies exist, and we chose some of the more popular ones to test against our simulation. Epsilon Greedy will select the arm that has historically performed the best, except for a certain percentage of the time designated by Epsilon, where the strategy will randomly explore another arm. Epsilon Decreasing is similar, but with a decaying epsilon value. And the upper confidence bound, or UCB1 algorithm, considers the average and standard deviations of past rewards for each arm and chooses the arm with the greatest potential reward. We also ran variants of Epsilon Greedy and Epsilon Decreasing that incorporated a regression oracle, discussed in further detail in another paper. In short, rather than using the mean of past rewards to predict future values for an arm, we set up a linear regression model that includes the chosen arm as a feature. We performed 3 sets of experiments on our simulator, each consisting of a series of trials in which a given strategy guided the experience for a simulated player through a 21-step period, reflecting our anticipated 3-week user study. The rewards received by the strategy were averaged across all trials at each step to create a time series that we could then graph to visualize their relative performance. Some of these strategies require a special parameter to be tuned for optimal performance, such as the exploration constant C used in the UCB1 algorithm. Therefore, our first simulator experiment was a battery of tests exploring various values of C and epsilon to discover where each strategy was best tuned for our expected user scenario. Note that finding the proper values for these parameters is critical to the performance of the AI, but doing so would not have been possible in a live user study. Our second simulator experiment ran trials for each of UCB1, epsilon decreasing, and epsilon greedy strategies using the optimized parameters. The results, shown here, suggest that UCB1 holds an advantage over the others tested so far. Our third simulator experiment was exploratory, investigating two techniques for so-called short horizon bandits, namely the regression oracle mentioned previously, as well as a forced exploration period that establishes a statistical baseline for each arm up front. The results are shown here, revealing that the regression oracle variants were especially effective in the case of our scenario, even outperforming UCB1. We used these simulator experiments to determine our bandit configuration for the user study, an epsilon decreasing strategy with a regression oracle and a forced exploration period of 9 steps. We then deployed it in a user study, where participants logged onto a web application each day to view profiles, report their motivation, and so on, as described earlier. 53 participants enrolled, and of the 48 who completed the 3-week study, 23 were in the experimental condition, where the AI agent chose the profile configuration each day, and 25 were in a control condition, where the configuration was selected at random. Results are shown in this table, where participants in the control group saw an average of 42 extra steps on the days of their sessions, compared to 160 extra steps for participants in the experimental group. This was not found to be significant, but it perhaps represents a trend. However, the change in motivation before and after the comparison activity did demonstrate a statistically significant difference in favor of the experimental group. The results of our user study, both the increase in steps and the statistically significant increase in self-reported motivation, suggest that our bandit-driven intervention was more effective than random assignment when selecting effective social comparison targets for users. This also supports our approach of defining a player modeling problem as an MAB problem and solving it with bandit techniques, and we believe that this could be a promising approach for adaptive games. Finally, in this research, we promote the use of simulations when designing an AI-based intervention, which allows rapid exploration of the potential options for the AI prior to a more resource-intensive user study. With a focus on designing virtual players that exhibit the salient qualities anticipated in real human players, researchers can gain better insight for their AI's design. Once again, I am Robert C. Gray, and speaking on behalf of my co-authors, thank you very much for your interest and your time today. We are also grateful to the National Science Foundation for helping to fund this work. Please feel free to reach out with any questions or comments, and I look forward to hearing from you.
Thank you, Robert. We have time for a few questions if anyone wants to either type in the chat or unmute themselves. Well, I have one question. So you talk fairly generally about adaptive games. Do you have a particular subset in mind? Like, could this work for any game, or you can like RTSs, board games? How general is this?
Well, it's one of the problems that we still have of applying this broadly to games is that it's, when we're working with extra games, we can take advantage of metrics like the steps that they walk or, their motivation or something like that. But if you're really trying to make a game that is pleasurable to a player, getting that information about their affect as a result of the experiences is a little more difficult. I know a lot of people are doing research in that area, but to keep it simple while those problems are still being investigated, we are applying it to extra games strictly because we have that advantage of those metrics coming back.
Oh, thanks. Makes sense. Last call for any other questions. If you don't want to ask them live, or you can again go to the Discord for post-conference questions. And
definitely.
Okay, I guess thank you again, Robert, and I guess we'll move on. The next paper, which I type in the chat here, actually has two of the same authors from the previous paper, Jichen Zhu and Santiago Tanyon, both from Drexel, and this is the AI Track's nomination for best paper at the conference. There were actually lots of great papers in the AI track, and so we had to pick one, though. Each track can nominate one paper. And this one is giving a broad view of the open problems in AI for automatic game personalization.
Hi everyone, I am Jichen Zhu. Today I'm here to present my paper with Santiago Tanyon. The title of our paper is Player-Centered AI for Automatic Game Personalization. We are at the dawn of mass personalization. Every day, we consume products suggested to us by recommendation systems. We find out what is going on with our friends and in the world through content feeds curated for us individually. In games, we're no strangers to adaptive systems. Personalized games have been developed, for example, to improve learning and for making better player experience. In this paper, we use Bake's definition for personalized games. This is a typical diagram we often see about adaptive game systems. Here, you have a game engine, a player modeling unit, a game adaptation unit. You also have a game state that is constantly being updated. These units interact with each other in order to best adapt the gameplay for a player. These diagrams are very useful, but what they're designed to do is to black box the player and white box the system so that we can study the latter. In this paper, what we attempt to do is to switch the perspective from the system to the player. This paper makes two key contributions. First, we reframe existing AI research on adaptive games through a player-centric cognitive perspective. Second, enabled by our new perspective, we identify 8 open problems. In this talk, I will first describe our theoretical framework. Given the time constraint, I will only focusing on 3 open problems. More details can be found in our paper. Our framework is Norman's cognitive theory on the structure of action. This is Norman's theory. For the purpose of our paper, we will simplify this into 5 steps. And here, the world, in this case, is our adaptive game system. Let's start with goals. A goal is something to be achieved. An example is, I want to watch a movie. Our goal is then translated into an intention to act. One possible intention here can be to find a good movie on Netflix. In the next step, our intention is turned into a concrete sequence of actions that can be executed. This can be going to my queue in my Netflix account and browse. After that, we perceive what has happened and interpret it. For example, does Netflix seem to suggest movies I like? Finally, we compare what has happened to what was the goal. So in this case, do I have a movie to watch? If not, this cycle may continue. Notice that compared to the system diagram we saw before, here the player is expanded while the system is black boxed. A couple more things to notice, particularly relevant to this talk. Notice the bottom 2 actions are observable, whereas the top 2 are not and must be inferred. So let's use it as a framework to examine the state of game personalization research from this player's perspective. First, gap of intention. There is currently a wide gap between what a player intends to do and what the adaptive system may think what her intention is. A common approach to infer intention is player modeling. The idea is to model certain aspects of the player that is particularly relevant to adaptation. The game AI community has developed a large body of work on player modeling. However, the gap of intention persists. For instance, this player talked about his experience of playing Silent Hill, Shattered Memories, an adaptive horror survival game. Early on in this game, the player got lost inside a side location. The game AI mistakenly interpreted the player going through every single object as his intention of wanting to spend a lot of his time there. As a consequence, it adapted the rest of the game heavily based on this misinterpretation. Unfortunately, gap of intention like this can very negatively affect players' experience. In the paper, we identified 2 open problems here. For the sake of time, I'll only talk about the second one, which is how to reconcile theory and data-driven models. This is an adaptive game we built for learning earth science. It was designed based on a learning theory of whether a player is primarily driven by external goals in the game, such as beating the game, or by self-driven exploration. According to the theory, this play style, which is a proxy to players' intention, is a stable trait and should not vary inside of the game. However, when we collected player traces and used machine learning to predict their play styles, we didn't get good results. When we looked further into the data, it turned out that the reason why our model didn't work was because players changed their intention throughout the game. As you can see from this alluvial diagram, in the beginning, most players were exploring, and towards the end, they focused more on how to beat the game. This example illustrates the tension between theory-driven and data-driven approaches for player modeling. When the results don't match, like in our case, it can be difficult to know where the problem lies. Is it because the player modeling algorithms doesn't work? Or is it original theory that was not built for this level of granularity? Because our intention can only be inferred based on our actions, what we can and cannot do in adaptive games are crucial. Currently, there is a large gap between what we can do in games and what we truly want to do. In most games, players are used to wrestle between their true actions and what they are able to do. A main reason for the gap of actions is because choices are expensive. For adaptive games, it is particularly important how we design these player choices. Here, I'll talk about Open Problem 3, minimizing systems' biases towards certain choices. This is a STEM learning game called Avian. In this game, the player learns bird watching by locating birds, taking pictures of them, and cataloging them in the game. Our research goal for Avian is to see how different types of learners may behave differently. We use the same learning model of goal-seeking versus exploration-based player styles. Very quickly, we run into a problem. From initial testing, we saw that almost everyone was a goal-seeker. How can this be? It turns out, for the player modeling to work, we needed the players to be able to freely express their natural learning inclination. However, our game heavily favored goal seekers because this group, by definition, aligns well with the building rewards and the goals of the game. If you are an explorer, on the contrary, there weren't a lot of things for you to do or rewards for your actions. What this means is that our game design is accidentally rewarding goal seekers and punishing explorers, and therefore skewing our data. After realizing this, we rebalanced the game and added more content to support explorers. The takeaway here is that all games have its built-in reward system. Designers of adaptive games need to make sure that action important to tell the players apart need to be disentangled from this reward system. 3. Gap of perceptions. Assume we have a perfect model of the player and all the right and balanced options for her to select. Now the player selects her true action. How can the game offer the best adaptation that is perceptible to the player? This community has developed many approaches to game adaptation. For example, planning-based approaches and drama management-based approaches. Another prominent direction is procedural content generation. The two key open problems here are automatically assessing the quality of the generated content and increasing the controllability of it. 4. Gap of evaluation. This gap happens when users cannot evaluate whether or how a system is adapting to them. You might be thinking, when an adaptive system really works, should an average user just enjoy the smooth ride that's made for her? Evidences from different adaptive systems, such as Facebook, suggest the opposite. When users don't know if or how a system is personalized for them, they cannot make informed decisions of how to best use it. Sometimes They form incorrect folk theories that led to low performance or even sometimes negative real-life consequences. In games research, how to help players establish appropriate mental models of game adaptation is still a research topic in its early stage. After the player evaluates the personalized adaptation, she checks to see if she has met her original goal. The big majority of the work in adaptive games focuses on meeting one person's immediate goal. However, we are already starting to see the negative consequences of this approach. The most visible of them are in social media. There is a growing concern that over-personalization has led to filter bubbles. Our final open problem is how to make adaptive games consider the goals of multiple players. For example, when we have a multiplayer exer game, which player's goals should AI take into consideration, and by how much? How does the AI reconcile an individual's changing needs at different times? And what does it mean to be fair? Our research group has recently started working on an experience manager for multiplayer games. But a lot more research is needed to turn the current individualistic way of thinking about personalization to a more community-based approach. In conclusion, we developed a player-centric framework to map current research in adaptive games. This framework follows the cognitive steps any person takes, and thus can help us to better understand player needs. Thanks to this framework, we identified 8 open problems we think are key to pushing the boundary of personalized adaptive games. We want to thank NSF for supporting this work and thank our talented students.
Thank you, Ji-Chen. There's a lot going on in that paper. Does anyone want to ask a question about some part of it? Got something in the meantime. So the last part was interesting where you talked about filter bubbles and multiplayer adaptation. In addition to multiplayer adaptation in one game, is there kind of an issue of a lot of games, people talk about them, there's kind of a meta, there's community around them. If games get too adapted, is there some kind of problem where people won't be able to talk to each other anymore?
That's actually an interesting point. I guess in this paper, we didn't look at like the meta gaming level, right, of games, like the communities around games. We were focusing on the interaction of a player with the game itself. But yeah, you have points. So probably decisions in the systems or in the AI in games affect things beyond games, right? Like as you were saying, how do people even report or talk about these games and their experiences? So probably that's actually another open problem that actually was a little bit out of the scope of the framework that we presented in the paper. But yeah,
that's fair enough. Yeah, thanks. All right, let me find Phil. There's a lot of participants, which is good, but that means I'm not finding Phil.
I think you can search in the participant tab.
Yeah, yes, all right. So Phil had a question.
Hi, yeah. I wanted to ask you about the sort of models you're using for the personality types, because it seems like that's actually quite an important sort of factor for a lot of these kind of works. It's been my experience that a lot of people try and identify individual types, and part of the problem is that from most of the work that I've read is that that's actually not the way to see things, and it seems like your experience has actually played that out, right, where you narrow down a particular behavior to a particular type of person, but in fact everybody's everything at different amounts at different times during the play cycle. So how do you adapt to that changing sort of personality role or changing play style in a way that actually predicts anything useful?
Yeah, that's an excellent question. And so in the part of the talk where Ji-Chen was presenting this game called Solving the Incognitum, So we exactly had that problem where the theory said that this player types, as you were saying, were traits, right? That where a player was either type A or type B, but we actually saw that they were states, not traits, right? So they were changing over time. So that was challenging because it is hard enough to predict a player type based on just the way they play, let alone if their style changes throughout the game, right? Like, how can you even do accurate player modeling? So we, from an algorithm point of view, we managed to get more accurate predictions by incorporating a time component. So we had a sequential machine learning approach that significantly improved accuracy, informed by the general trends that we saw in that alluvial diagram that Jichen was presenting, where we knew that in average, this percentage of players from this type of the game switched to this other type in the second part of the game. So knowing this type of information actually really helped us with player modeling. As for how to then adapt, that part we did not study that much, but that is a significant challenge, because if you predict that your players type A, but by the time you act, they're already in type B, right? So that is a bigger challenge. We only focused on the player modeling side there, but it was already challenging enough. So yeah, that's a big problem.
Yeah, I just want to follow up. I think it's a definitely excellent question. I think I want to go back to the thing I think I was talking about in the video, right? So we are, especially in the game AI community, we rely a lot on existing theory in terms of learning, in terms of personality, the psychology theories. So most of those theories sort of like, it's kind of like a black box, and we try to use our AI personalization or player modeling in order to make use of it. But I think the challenge here is a lot of these theories kind of are built on data they collected from just like one shot questionnaire, right? So they don't have the same kind of granularity that we now suddenly face thanks to sort of this like online collection of data. So I think there is definitely this kind of conflict between these theoretical based approaches that was maybe built from a different type of data, different kind of access to understanding human behavior, to now suddenly we're trying to build our player modeling, the AI part, using the theory, but then also enable us to see some of the things that the previous theories don't see. It's a really interesting challenge there.
Thanks, Santi and Jichen. We need to move on to the next paper, but there were two more questions, but from Max and Julian, if you want to continue it offline, either in the chat or the Discord chat. But in the meantime, we're going to move on to the last paper of the session, so we don't hold up the whole conference. It's great. There's a lot of interesting stuff coming out there. The last paper, though, is moving a little different direction towards two-player game playing algorithms, a new algorithm called opponent pruning paranoid search, which generalizes some of the current state-of-the-art methods in that area by Hendrik Beyer and Michael Keizers, who are both at the CWI Research Institute in Amsterdam.
Hi everyone, I'm Hendrik Beyer, and this talk is about some work I've done with Michael Keizers on a search algorithm called opponent pruning paranoid search. This work is primarily applicable to deterministic perfect information multiplayer games, that is, games with more than 2 players. In the following, I'm going to quickly outline the state-of-the-art minimax-based search algorithms for these games, as they form the baselines for our later experiments. The classic multiplayer approach named MaxN search is based on the idea that every player at every internal node of the search tree maximizes their own individual utility when it is their turn. So when you look at the leaves of this toy tree, you'll see that every leaf node is labeled with a vector of utility values for the 3 players, and every player chooses a move that maximizes their own utility whenever it's their turn. Now, MaxN is very intuitive and converges to an equilibrium in the limit, but it has 2 major weaknesses. First, deep pruning, like in 2-player alpha-beta search, is not possible, leading to pretty shallow trees. And second, MaxN can be too optimistic, because it assumes that no opponents ever form coalitions against the root player. Paranoid search takes the opposite approach, of assuming that all opponent players always form a coalition against the root player. This effectively turns any multiplayer game into a two-player game between the root player and the coalition, which makes deep alpha-beta style pruning possible. As you can see in this toy tree, the vectors are gone because only the utility values for the root player matter here, which are maximized by the root player and minimized by her two opponents. Paranoid tends to outperform Max N in practice due to the deeper searches enabled by alpha-beta style pruning. However, it suffers from being overly pessimistic, especially with deeper searches and with higher numbers of opponents. In many games, it's ultimately not possible to win if all opponents form a coalition against you. Two improved algorithms based on paranoid search are Best Reply Search, BRS, and the current state-of-the-art BRS+. These algorithms still assume that all opponents are playing against the root player. However, they restrict the move choices of this coalition. In BRS+, only the opponent with the strongest move against the root player can choose this move freely, while all other opponents have to choose the move ranked first by a move ordering heuristic, and so have their branching factor reduced to 1. In this toy tree here, the highest ranked move at every node is marked in bold, and you can see that between any two nodes of the root player, at most one opponent is allowed to choose a different move. This restricted move choice of opponents allows for even deeper search and more long-term planning than in vanilla paranoid search, and it also weakens some of the pessimism of the paranoid assumption. All opponents are still playing against the root player, but their moves and therefore their strength as a coalition are somewhat limited. BRS+ is currently the state-of-the-art Minimax-based search algorithm for fully observable deterministic multiplayer games. The new algorithm we are now proposing, Opponent Pruning Paranoid Search, or OPPS, is a direct generalization of it, as I'm going to explain on the next slides. BRS+ essentially divides the opponents of the root player into two groups. One group of only one opponent who is allowed to freely choose a move, always the one opponent that can hurt the root player the most, and another group with all other opponents who have to play their highest ranked move. OPPS generalizes this by introducing three parameters. N1 is the number of opponents in the first group with the wider move choice, which is always 1 in BRS+, but is the first freely tunable parameter of OPPS. L1 is the corresponding upper limit to the branching factor of this group, which is infinite in BRS+, but gives us the second parameter of OPPS. And L2 is the upper limit to the branching factor for all other opponents, which is always 1 in BRS+, but represents the third parameter of OPPS. L2 is always smaller than or equal to L1. So just to clarify, both L1 and L2 here are limits on the number of top-ranked moves as ordered by the static move ordering. For example, L1 equals 8 means that the first group of opponents can choose from the 8 highest-ranked moves. As you can see here, the existing BRS+ is simply a special case of OPPS, with fixed parameters 1, infinity, and 1. By varying these three parameters, however, OPPS can more smoothly adapt both its degree of tree pruning as well as its degree of paranoia, or flexibility of the opponent coalition, to whatever works best in the domain at hand. Now, depending on its parameter settings, the tree searched by OPPS can be either larger or smaller than the tree BRS+ would search. This is illustrated on this slide and the next one with the tree searched by two different OPPS parameter settings. In this toy tree we can see that while the BRS+ tree we've seen before had 10 leaf nodes in total, this one, the OPPS 1 infinity 2 tree has more leaves, 16. But the OPPS 0x2 tree, where the value of x doesn't actually matter, has only 8 leaves. And these small differences in tree size grow exponentially with tree depth, and really influence playing strength, as I'm going to show on the next slides. So let's get to our experimental results, with OPPS playing against the baseline algorithms, and some further analysis of what these three parameters really mean for search tree growth. The test domain for all experiments reported in the paper is Chinese checkers, because it's a relatively well-known multiplayer board game which allows to scale the number of players from 2 to 6. However, I am hoping to soon have results ready for a number of other games as well. All data points are based on at least 1,000 games, and all experiments used a fixed time per move search. The algorithms were therefore implemented with iterative deepening. Our experiments are divided into 3 sets. In the first set shown here, OPPS was compared to its special case, the current state-of-the-art multiplayer search technique BRS+. We use time controls of 50, 250, 1000 and 5000 milliseconds per move in Chinese checkers with 3, 4 and 6 players. The parameters of OPPS were tuned for each playing condition separately. As we can see in this chart, OPPS is significantly stronger than BRS+ in all game variants and time controls, with the exception of the 3-player game at 250 milliseconds where the difference did not quite reach significance. We can make 2 more interesting observations here. First, OPPS is able to scale better than BRS+ with the number of opponents. The average performance over all time controls increases from 3 to 4 to 6 players, as you can see at the bottom. This is very promising for future work on domains with even higher numbers of players. Second, the performance of OPPS can vary quite a bit with the time controls, something we discuss in more detail in our paper. Now, the baseline we just used, BRS+, has been shown to be a significant improvement over MaxN and Paranoid in the literature in a variety of games. However, we wanted to make sure that our tuning of OPPS against BRS+ had not led to overfitting, and that OPPS was indeed still outperforming the older techniques MaxN and Paranoid as well. In our second set of experiments, we tested this at 250 milliseconds per move, with the same parameter settings that were found to be optimal against BRS+ before, without retuning anything. And we indeed found that OPPS is much stronger than both MaxN and Paranoid in all variants of the game. The third and last set of experiments finally looked at how fast search trees grow with search depth. We used 4-player Chinese checkers here, and we compared MaxN, Paranoid, BRS+, and 2 other variants of OPPS, namely OPPS 151 and OPPS 1∞2. The resulting average search tree sizes for different search depths are plotted in this figure. It shows how much smaller search trees for the same depth can get when moving from MaxN to Paranoid, and then again when moving from Paranoid to BRS+. And the additional plots for OPPS 151 and OPPS 1∞2 show how the parameters of OPPS allow it to fine-tune the tree sizes to what works best in the domain at hand, being able to do both more or less pruning than BRS+. And this brings me to the last part of my talk on possible next steps. We see several interesting directions for future research on multiplayer games here, so let me just briefly mention 2. First, the design of OPPS could be generalized further to make it even more flexible and adaptable. Instead of only using 2 groups of opponents with a fixed size and a fixed branching factor limit each, we can easily imagine a generalization to more groups, maybe even in an algorithm that makes the choice of branching factor in every node of the tree dynamically based on features of both the game state as well as the current state of the search. This idea could also be generalized to games, for example, featuring indeterminism, simultaneous moves, or imperfect information. We see OPPS only as a first step here. And second, the idea of abstracting away some of your opponents or some of their move choices in order to be able to focus more on your own planning is also promising to explore more deeply in the context of the Monte Carlo tree search framework instead of the Minimax framework. In MCTS, for example, alpha-beta style pruning is not possible, and the paranoid assumption has not been shown to work yet, but abstraction and pruning or unpruning of moves have been studied in some depth. We now actually already have a paper out on this translation to MCTS published at this year's Conference on Games, so please do check that out as well. And that's it. Thank you very much for listening, and I hope to see a lot of you in the Q&A session later. Goodbye.
Thank you, Hendrik. We have time for maybe one question before we wrap up this session. No questions. If you have any, I saw Hendrik, you just unmuted. If you have any comments you want to make or follow up. Okay, well, we should wrap up then. This is the first of the 4 AI sessions that we're going to have over the next few days. And thanks everyone for coming. And yes, that's it.